Light. We've been investigating light. Its broader sense. Now, I want to use light as a stepping stone into one of the most important aspects of science, the nature of science. And that is its reliance on a long memory, a history, recording material and data and images over time that we can refer to and that can be built on over generations. And also, the other really important aspect of science, which is the use of and application of our capacity, our human capacity, to imagine. Now, light is the phenomena. This is what happens. And we want to understand it. This seeing that we're doing, or the energy caught in photosynthesis, or the energy changes in chemicals on our anthotypes, or the energy changes we're going to work with our photo imaging, is a way of capturing that light. So this is the capture, the and the translation or transference of that information. And the image is fixing that and storing it, and the idea of memory. And then our imagination is our making meaning. Yeah? Connections. And also applications.
We started our light topic looking at waves. Some of the earliest 18th century attempts to really get to grips with wave behaviour were done by imagining a plucked violin string vibrating. The visualization could freeze the wave, but also ask questions, which led to the wave equation. The descriptions and predictions of the theory of the wave equation synthesized well with the observed and experienced world. It led to big advances in our understanding of water waves, sound waves, and predicted the idea of electromagnetic waves. To understand what the wave equation does, imagine yourself in the middle of the ocean. As the waves pass by, you bob up and down, and as time passes, the rate at which your height changes is a derivative of your height with respect to time. At the top or at the bottom, your height isn't changing, it's zero, and there's no acceleration, zero acceleration. But in between, you can work out a value for the slope from a derivative of the wave height with respect to space, down, up and down. The acceleration rate of change is affected by the force caused by nearby segments. We can think of ocean waves. It's very easy to see them. But how did we ever get to thinking of light as some kind of wave? How did that come about? Michael Faraday was a self-taught practical scientist who, amongst other things, applied the link between electricity and magnetism to invent the electric motor and inspired the use of electromagnetic induction and electric telegraph, which led to the invention of the telephone. But it wasn't until James Maxwell imagined electric fields and magnetic fields as invisible fluids that equations describing and predicting the interaction of electricity and magnetism in such devices were developed in the 19th century. It is easier to visualize this theory as two interactive waves, both travelling at the speed of light, and therefore the implication is that light is an electromagnetic wave.
There had been no reason before Maxwell's equations to imagine this fundamental link between light, electricity and magnetism. So now, experimentalists could imagine and search for new electromagnetic energies as yet undiscovered, such as radio waves, microwaves, X-rays. Using his imagination, Maxwell was able to reach a new improved description of reality. make more meaning. And this new understanding inspired new ways to think about light. In his lecture, Solutions of Maxwell's Equations in Free Space, Richard Feynman pointed out that science makes huge demands on the imagination. Not only that it requires us to use imagination, but that science also requires us to do so in a very careful, responsible way. Whatever we are allowed to imagine, whatever imagining we use in science, must be consistent with everything we know.
Feynman goes on to ask, can we imagine beauty we cannot see? Everybody says, oh, a rainbow. We experience as we see it as beautiful. Is the graph of the electromagnetic spectrum beautiful? Do we have enough imagination to see in the spectral curves the same beauty?
In 1979, in his New Zealand lecture series, Feynman stated that science is about synthesis, pulling it together. It's about the theory and the phenomena. The phenomena and the making sense, the theory, theoretical. And it's the synthesis of these together that builds our understanding of the natural world through science. An example of such a synthesis, of course, Maxwell's electromagnetic wave that helped explain the phenomena that Faraday explored and revealed with his electric motors and so on. The theoretical and the practical building together. The problem often is to fit the theory to explain reality, and this synthesis often takes us into realms of reality we cannot directly see, realms we can't experience on our human scale. Starting with Rutherford's experimental work leading to a new visualization of the atom as being mostly empty with a dense nucleus and sparse electrons, there was a struggle to synthesize the phenomena with theory when Maxwell's wave theory of electromagnetism didn't fit the observed interactions of light and electrons. Now, in a modern scientific synthesis, we have come to the point where we need to imagine light as particles, photons operating in a probabilistic quantum reality. And in the 20th century, we have to think within the framework of the new standard model where the photon is the boson, the energy carrying particle for electromagnetic energy. The theory that now synthesizes this with real world phenomena is quantum electrodynamics, QED, which brings relativity, probability and quantum mechanics together to describe and predict almost everything we experience, except radioactivity and gravity. It describes how light and matter interact. It's weird. I don't understand it, but it is beautiful.
How then does our experience of the classical world emerge from an underlying quantum one? A ray of light hits the surface of a smooth sea. In the classical world, we construct from our experience the reflected rays bounce off at the same angle as the incoming rays. Some rays may be refracted through the air-water interface, some are absorbed, some scattered, but this is not what happens in the real quantum world. Visualize the ray of light as tiny quanta of energy, photons travelling all possible paths that they can. At extreme speed, the speed of light, each photon is absorbed and re-emitted by the electrons of the matter they encounter. Feynman illustrated these events with what are now called Feynman diagrams, such as this one, where a straight line path is an electron and a wriggly line is a photon. These events can happen in all possible ways, in all possible directions in time and space, but if you superpose them all, these possible events, the overwhelming proportion of the emitted photons travel pathways at angles that allow us to measure the truth of our macro human scale world. The angle of reflection is equal to the angle of incidence, and angle of refraction is a function of the relative refractive index of the material encountered. Here it's water. Similarly, these photon-electron interactions at the quantum level result in the observed colours of pigments and the chemical processes involved with vision and photosynthesis.
Quantum electrodynamics is the most accurate and precise descriptor of reality that we know of at the present time. The latest figures, 21st century, that I could find show that the synthesis of theory with phenomena is remarkable. The latest experimental values come out at, this is experimenting and measuring the magnetic moment of the electron, 1.00115965 eh? And using the quantum electrodynamic theory, the mathematics, which the Feynman diagrams are visual representations of, the theoretical value of the magnetic moment of the electron is 100115965282032. Absolutely remarkable. So this is sort of accuracy that would be similar to measuring the circumference of the world within the accuracy of the thickness of a single hair. Vision is our dominant sense. It's, stuffs our lives with experiences and phenomena, ideas and meanings, and built-in pattern seeking and metaphor making that our brain automatically does, our Pleistocene brains deal with, doesn't always make a coherent sense of all that we experience. Human science operates within those constrictions, that framework, as best it can. Our remarkable capacity to imagine enables us to create new images and new ideas, new tools and new understanding. But without synthesis to a verifiable memory, without care and integrity, accuracy and precision, aligned with observable and tested evidence within a shared understanding, we can lose ourselves. In a time of global pandemic, a time of unprecedented climate change, now more than ever, we need to look to science, for the long memory of science that gives us to see what is happening to our world, our ocean world, and to imagine a safe and sustainable future. The next challenge is for you to make a tool that is capable of making a photo image, a light image, a memory store of some phenomena. And using your imagination, share that with us. Something connected to the sea, an idea. Wave, pathway to the beach. We'll see you in the next video where we're going to make a camera.